Hello and welcome to the chopper controlled DC drives practical of semester 7. First, let's identify the objectives of our lab session: to measure speed control characteristics of the chopper drive, to study the armature and field circuit waveforms of the motor, to study the basic control strategy, and finally to study the operation of control circuit. Now let's have a look at the equipment used in our practical. Before moving to the practical, let's identify the theoretical background of our practical. What does a chopper circuit mean? A chopper is a static device that converts fixed DC input voltage to a variable DC output voltage directly. Choppers are used to get variable DC voltage from a DC source of fixed voltage. Self-commutated devices such as MOSFETs, power transistors, IGBTs, GTOs, and IGCTs are used for building choppers because they can be commutated by a low power control signal and do not need communication circuit and can be operated at a higher frequency for the same rating. Chopper circuits are used to control both separately excited and series circuits. Now let's have a look at the chopper circuit used in this lab setup. In this diagram, TH1 is the main thyristor. The commutation circuit comprises of TH2, which is the auxiliary thyristor, capacitor C, inductor L, and diodes D1 and D2. When the main thyristor TH1 is turned on, voltage VDC is applied across A and H, that is, across the armature. When TH1 is turned off, if the freewheeling diode conducts, zero voltage appears across AH, and if the freewheeling diode ceases to conduct, the back EMF of EB appears across AH. Now let's have a look at the theoretical voltage and current waveforms at the load. The first figure shows how discontinuous current appears across the load when the T on is less than T off. Here the load current increases exponentially during the chopper on time and it becomes zero during the chopper off time. Second figure shows how continuous current appears when the T on is greater than T off and the load current increases exponentially during chopper on time and decreases during the chopper off time. The chopper is switched on again before the current becomes zero. Actual waveforms can be slightly different due to stray circuit inductance. Next we will look into turn-off waveforms on an extended time scale. First we will look into the waveforms from T1 to T4. Here, the main thyristor TH1 is fired at T equals T1, so that load current and output voltage is IA and VDC respectively from T1 to T2. With the turning on of TH1, commutation circuitry remain inactive. Commutation process begins with the turning on of TH2. At T2, TH2 is fired through the gate and is turned on. As T2 is on, the capacitor inductor series circuit is short-circuited and so the capacitor is charged to negative voltage minus VDC. The voltage across TH1 is VDC until T1 and the voltage across TH2 is VDC until T2. When we look into the current waveforms from T1 to T4, the current through the TH1 remains at IA and the current through TH2 increases when TH2 is on and it becomes zero as the capacitor gets fully charged while load current remains at IA. When considering time from T4 to T5, the capacitor C is fully charged at T4 and current reverses, and so TH2 is turned off at T4. When the capacitor is charged, it provides minus VDC voltage reverse bias to TH2 thyristor, so TH2 is turned off. The capacitor charged to negative VDC pushes current IC opposite to TH1, so the resultant current through TH1 reduces. Here, IC does not flow through the D2 diode because the forward voltage of the diode is more than that of the drop across the thyristor TH1. When considering T5 to T7, the capacitor current turns off TH1, so the impedance offered by TH1 is more than the diode and the current IC flows through the diode D2. Then the current IC slowly decreases, and when IC is equal to IA, the diode D1 current becomes IA, and as C is overcharged, D1 is no longer forward biased, so the diode is turned off. Now let's consider the time above T8. Capacitor is charged to plus VDC and C is overcharged. The freewheeling diode is forward biased and VO is reduced to 0. IA current is now equal to the current through the freewheeling diode. The commutation period is complete. Then TH1 can be turned on by a gate pulse, and again TH2 is turned on. Capacitor charges to negative potential and this cycle repeats. Now let's get an expression for the circuit turn-off time of TH1. Let TO be the circuit turn-off time for TH1 and TO is half period of LC resonance circuit. So simple TO is equal to capital TO minus 2 times T5 minus T4. That is our equation 1. This diagram shows the control unit of the system with operational amplifiers and comparators. This system uses the armature voltage feedback in the place of speed feedback, as the armature voltage is proportional to the speed. The armature current feedback is used to compensate for the armature resistance drop stability reasons. For setting up purposes, 5 potentiometers are provided as shown. These diagrams show the gate waveforms in the control unit and shows how TH1 and TH2 are triggered. Finally, let's have a look at the speed control characteristics of the DC motor. The response of the DC motor depends on the average armature voltage and the armature current, as the mechanical system cannot quickly respond to ripple components. This is the lab setup we will be using for this practical. We will identify its parts gradually in the video. In order to begin the practical, first we have to switch on its power supply from the panel located behind the setup. Then we switch on the main breaker on the panel and the start button, which is the black one. The red one is for stopping. Part A of the practical. On the unit you see in this photo, there are 5 knobs and each knob is for a potentiometer. We will set them as mentioned in the lab sheet. 2 and 4 in the middle, first and third at minimum, and finally fifth one a little bit low to the middle. Moving on to part B. First, we adjust the rheostat to 25 ohms. For that, a multimeter is used. Now we will measure the chopper input DC voltage using the cables as shown. This is done using a multimeter as well. You do not have to note down these measurements. We will provide them later in the video. This is the circuit for part B. The ammeter, then we have the voltmeter and the rheostat, which is set at 25 ohms. And finally, we have two terminals A and H for the armature. For this part, we must get some oscilloscope plots as well. It is connected in parallel with the voltmeter. Now we will increase the speed input potentiometer step by step and get ammeter and the voltmeter measurements for each step. Now the potentiometer is in the step 0. Moving on to step 1. Now to step 2. Notice how the meter gauges move. Now third step. Now to the fourth step. Step 5, Step 6, Step 7, now Step 8, Step 9, and finally Step 10. While taking measurements from the voltmeter and ammeter, we must also use the oscilloscope output to observe the on-state duty cycle. Here are all the values for part B. Now let's move on to part C. As shown in the circuit diagram, we use two ammeters and two voltmeters, one on either side of the circuit. A and H are armature terminals and J and K are field terminals. We also use a rheostat set to 11 ohms for the armature side and a one set to 25 ohms for the field side. In this next part, to measure the rotating speed, we will use a tachometer. Just like in part B, we will increase the speed input potentiometer step by step and take measurements. Here are the measurements obtained for each step. We have to connect the oscilloscope CTs as well for this part. The CT is connected to one of the cables on the ammeter and the other side is connected to the oscilloscope as shown. After switching on the chopper, we set the speed input potentiometer to step 7. Then we obtain a couple of plots. First, the armature voltage and current waveforms. Then, field voltage and current waveforms. Moving on to the final part, part D. On the unit shown here, there are a few contact points. Let's see what those contact points give as an output. Now, using the oscilloscope, we obtain the waveforms of all the others compared to CT1, which is the pulse generator output. The plots saved from the oscilloscope are as follows.